A standard pip install for version 4.87.2 triggers a hidden sequence. As the installation logs scroll, the software begins mapping the host environment and establishing connections to the surrounding cloud infrastructure. The target in this attack is the official Telnyx PyPI package. It is a widely utilized Python software development kit that engineers use to integrate VoIP, SMS, and WhatsApp messaging directly into their applications. Because it acts as the core communication bridge for countless software projects, the Telnyx package records over 740,000 downloads every single month. That massive user base attracted a threat actor known as Team PCP. By securing stolen PyPI publishing credentials, they bypassed the repository's external security and authenticated directly as the legitimate maintainers. Operating from the inside, they pushed two specific malicious updates to the registry, versions 4.87.1 and 4.87.2. But the payload inside these updates did not look like standard malware. Team PCP engineered a system that bypasses detection by hiding its credential-stealing code entirely inside a standard WAV audio file. Trusting heavily relied-upon open-source SDKs implicitly creates a massive silent attack surface. By poisoning the supply chain at the source, attackers bypass traditional perimeter defenses entirely, ensuring their code executes from a position of absolute trust. The attack pipeline begins the exact moment a developer or an automated system types import Telnyx to initialize the library in their application. Looking at the package's file structure, the malicious modifications are isolated entirely within the telnyx/client.py file. The execution logic requires no further action from the user. The code is programmed to trigger automatically at the exact moment of module initialization. To evade immediate detection, the malware is designed to allow the legitimate SDK classes to load and function normally, splitting the execution path. Because the communication tools continue to work as expected, standard automated tests will not fail. Continuous integration and deployment pipelines will compile the application and push it to production without catching the anomaly. At the operating system level, the payload immediately spawns a detached process. This mechanically separates the malware's execution thread from the main host application. By piggybacking on the standard initialization sequence without breaking the underlying functionality, the malware achieves execution evasion and silent persistence from second zero. Once isolated in that detached process, the malware initiates a network extraction phase, reaching out to a remote command and control server. The server responds by delivering a payload disguised as a standard audio file, specifically named ringtone.wave, ensuring it looks like benign media traffic to network inspection tools. This hex editor view shows the structure of that downloaded WAV file. Notice that the audio headers remain perfectly intact at the top, allowing the operating system to validate it as a standard media file. The threat actor utilized steganography to conceal the actual payload, embedding malicious code directly within the audio data frames below the header. To extract the weapon, the malware runs a simple XOR-based decryption routine directly on the host machine, reconstructing the payload from the audio data. This extracted script executes entirely within the host's memory. It never touches the hard drive, leaving zero executable artifacts on the file system for antivirus tools to scan. Operating in memory, the script begins a targeted harvesting operation, seeking out SSH keys, cloud tokens, cryptocurrency wallets, and sensitive environment variables. Wrapping an XOR encrypted payload inside standard media data frames completely blindsides traditional static analysis and file scanning security controls. The threat actor did not rely on a signal execution method. The initial memory-resident payload contains advanced environmental awareness. This flowchart maps the primary logic branch. The malware first checks its surroundings, detecting whether the host machine is running within a Kubernetes cluster. If it finds a Kubernetes environment, the malware immediately enumerates the cluster, scraping the control plane for administrative secrets. It weaponizes those stolen secrets to rapidly deploy highly privileged pods across the available worker nodes. The ultimate goal of this lateral movement is to utilize those privileged pods to pivot downward, granting the attacker direct root access to the underlying host operating systems. However, if the malware detects that the initial operating system is Windows, the execution path shifts entirely. On a Windows machine, the malware reaches back to the server and downloads a different audio file, named hangup.wave. The extraction process for hangup.wave deploys a hard-coded binary executable named msbuild.exe, abandoning the memory-resident script approach used on Linux and Mac OS. To establish persistence, this binary is dropped directly into the Windows startup folder, ensuring the malware reignites every time the system reboots. To maintain stealth, the malware generates a local lock file. This restricts the binary's execution to only once every 12 hours, intentionally minimizing CPU spikes to avoid tripping performance monitors. This environmental branching transforms a single compromised PyPy package into a multi-headed threat. It is highly capable of executing both cloud-native lateral movement and traditional OS-level persistence, depending entirely on where it lands. Because the primary payload executes via a detached process and resides primarily in memory, simply running a standard package removal command is insufficient to clear the threat. Any system, container, or server that imported Telnyx version 4.87.1 or 4.87.2 must be classified as a fully compromised environment. The immediate safe harbor for developers is to completely purge the infected iterations and roll the environment back to the clean variant, Telnyx version 4.87.0. The incident response cannot stop at the codebase. Teams must address the likelihood that the malware successfully harvested active credentials and environment variables during its memory execution. Engineers must aggressively rotate all infrastructure secrets, cloud administration tokens, and SSH keys that were exposed to the compromised host. Rotating these secrets is a mandatory step, even if no network exfiltration was explicitly logged by the security team. The silent nature of the memory execution means the data could already be in the threat actor's hands. The Telnyx incident reveals how deeply a compromised SDK can penetrate an organization from the inside. By weaponizing the libraries that engineers trust for core communication, threat actors turn the development environment into a silent mechanism for dismantling infrastructure.